Hi, welcome to Team 13's Case Study 2. I'm Grania.
I'm Sebastian.
I'm Haley.
I'm Anvita.
The occurrence of blackouts, such as the one that occurred in Texas this year and in 2011, indicate that there is a need for continuing improvement in the efficiency and reliability of electrical grids. According to the New York Times, during the February 2021 Texas grid failure, natural gas, rather than solar and wind, was impacted the most by the extreme weather conditions. The accelerating effects of climate change are causing severe weather patterns to occur more frequently, and this trend puts electrical grids at further risk of failure. Expanding the use of renewable energy as a fuel source will help to gradually mitigate the effects of climate change. We aim to address the following research question with our findings. What is the optimal renewable energy grid in Texas to reduce the severity of future grid failures, carbon emissions, and financial cost? Our hypothesis is that growth in renewable energy sources incorporated into the grid will increase the reliability of the system, decrease the emissions produced, and be more cost-effective than the current system.
For our case study, we wanted to better analyze the relationship between the distribution of sources of electricity over time and the resulting grid reliability during a storm, carbon emissions, and financial costs, both consumer and infrastructure related. Our method of study is a predictive model that calculates these four variables over time based on a set of initial constants, such as construction costs per kilowatt, and user-entered parameters such as start and end year, and the initial percentages of sources. All of these initial conditions are shown in the top of the flowchart. Prior to programming the calculator, our constants were determined by analyzing data from the EIA, the U.S. Department of Energy, and the Railroad Commission of Texas. The model itself is based on a Python program using NumPy and Matplotlib modules to generate the graphs. The flowchart illustrates the order that the variables are determined. Each of our assumptions can be placed into one of three categories: infrastructural, relating to the construction of new infrastructure for the ERCOT grid; winterization, related to how the winterized natural gas is considered in our calculations; and production / grid-based, relating to how we will be calculating values dependent on the production and generation of energy. To view all of our assumptions, feel free to visit our website using the QR code.
In terms of results, the graphs shown in the center of our poster illustrate two scenarios which we tested and decided to highlight in order to compare investments in renewable energy versus fossil fuels. Scenario 1, shown in green, is similar to the current trends in the growth of renewable energy, with 1.5% per year increase for both solar and wind, but with an added second derivative of 0.5% per year squared. Scenario 2, which is shown in red, shows what may happen if there is no growth in renewable energy over the next decade, but instead investments are made into winterizing Texas's natural gas infrastructure, with a 1.5% per year increase in winterized natural gas and 1% per year squared second derivative. You can try out the calculator for yourself by visiting our website and view the scenarios there.
In conclusion, we found that no optimal grid was found within the three scenarios, as there are trade-offs between reliability, emissions, and cost. For least emissions and best reliability, the highest percentage of renewable energy should be implemented, while for moderate reliability and reduced cost, winterized natural gas is the preferred solution. Since our calculator is intended to be a predictive model, construction of new infrastructure can be planned accordingly via initiatives and legislation to shift the energy generation distribution over time according to the factors that are prioritized at that time. For example, if the goal is to reduce emissions or to increase reliability, increased growth in renewable energy production would help reach it. Whereas if the goal is to reduce consumer prices and construction costs, winterizing the natural gas infrastructure would help achieve it. These findings will be pertinent to areas looking to renovate their grid to incorporate renewable energy. Our case study focused on Texas's grid system in particular, but similar analysis for other grid systems would be applicable to plans such as the UMass Amherst Carbon Mitigation Plan's trajectory to 100% renewable energy by 2030, quantifying what blend of renewable sources would be the most reliable with respect to mitigating and preventing several grid failures. Thank you for watching our presentation on what we can learn from Texas grid failure.